Okay, so a quick review for those of you who are trying to catch up. We are doing a quick review of exponential functions, y equals a to the x, where it's exponential if the variable is in the base. Restrictions on the base: in order to call it exponential, that base has to be positive and not equal to 1. Because if it is equal to 1, we just get a straight line. You raise 1 to any power and you get 1. It's not that you can't do that, it's just that we don't call it an exponential function. We call it a linear function. Okay, for an exponential function, remember variable always in the exponent. Quick reminder of exponent laws: anything to the power of 0 is 1. When you have a negative exponent, it means you're taking the reciprocal. So, for example, 3 to the minus 1 is a third. 3 to the minus 4, 1 over 3 to the fourth, or 1 over 81. When you have a to the p over q, it means you're looking for the qth root of a to the p. So the denominator becomes the index on the root. The numerator is your power. It is always going to be easier to take the root and raise the answer to the power. For example, 64 to the 2/3 means you're taking the cube root of 64 squared, which is a really big number, and then you're looking for the cube root of it. It is easier to find the cube root of 64, which we know is 4, and then square the answer. Okay, when your base is between 0 and 1, because remember it can't be negative, you have exponential decay, meaning that your graph is going to be a decreasing function. Remember, how do we say decreasing? As I move from left to right, the y values get smaller. What does this look like? Well, let's do it in our head here, a little t-chart. If x is 0, anything to the 0 is 1. If x is 1, I get a half. If x is 2, I get a half squared, a quarter. And we can see what's happening is that this just keeps on getting closer and closer to 0, because we all remember from last year that the x-axis is our horizontal asymptote. So our horizontal asymptote along the x-axis, aka y equals 0. Okay, and if x is negative 1, I've got this. 1/2 to the negative 1 would be, what does the negative mean? Take the reciprocal, the answer would be 2. X is negative 2, I would get negative 2 squared, 4. Negative 3, 8. Okay, so exponential decay, the domain for all exponential functions, all reals, the range, y has to be greater than 0, strictly greater than. We're never going to get 0. That's our horizontal asymptote. We will always have this y-intercept. When x is 0, y is 1. Anything to the power of 0 is 1. Our base is larger than 1. What do we call this? Exponential growth. So you have an increasing function as you move from left to right. Your y values get larger. Quick sketch: exponential functions have a horizontal asymptote. Y is never going to be 0. We have a y-intercept at 1. That is, when x is 0, y is 1. If x is 1, I've got 2 to the 1. X is 2, I've got 2 squared. X is 3, I've got 2 cubed. X is negative 1, I've got a half. Negative 2, a quarter. Okay, so here's our graph of exponential growth. So decreasing function and increasing function. All the key features of that graph: domain, range, intercepts, asymptotes. So note that all of the graphs go through 0 and 1. If your base is a proper fraction, positive fraction, we've got a decreasing function, decay. If a is 1, it's just a constant function. We don't call it exponential. And if a is bigger than 1, increasing. Okay, so as long as a does not equal 1, we've got a domain from negative to positive infinity and a range from 0 to infinity. Exponent laws. So we learned these a long time ago in grade 8, grade 9. reviewed them in grade 10 and 11. When the bases are the same and you're multiplying, you add exponents. Make sure you're comfortable with exponent form, either going from left to right or from right to left. A to the power of x minus y means you've got a to the x divided by a to the y. I think when we first taught you this, we started here and went this way. Be comfortable going that way as well. A to the power of x to the y is a to the x times y. When you have a power to a power, you multiply exponents. And when you've got more than one factor being raised to a power, that power applies to both of the factors. Okay, so taking what we know about exponential functions, can you apply transformations to this one? So we're starting with that. We all know what y equals 2 to the x looks like. It's exponential growth. The base is bigger than 1. It has a y-intercept at 0, 1. So this is just the graph, a quick sketch. Put it in your notes. Y equals 2 to the x. You should be able to label two other points on there really easily. What would happen if x were 1? 2. And if x were negative 1? A half. Okay, so everything you remember about transformations, verbal description of the transformations, this compared to that. Well, I think in Math 12 we did this. We would have written it in this format, so it would be a little bit easier for us to identify that outside the function, we've got this plus 3, which moves it 3 up. That is going to take our horizontal asymptote, which was at 0, and move it 3 up so that it is now at 3. New horizontal asymptote. What does this negative do to the function? Y goes to minus y. I reflect it in the x-axis. When you get a reflection over the x-axis, everything flips upside down. So you should think about this graph as being oriented this way. Can we see it? Okay, do you remember how to do a mapping to get it to reflect in the x-axis and shift 3 up? What would happen to any point xy on this original graph under these transformations? Do we change anything with the x inside the function? Do I do anything to the x? So x is going to stay the same. What about y? Well, what did I do? I had to change the sign, and I want to move it 3 up. That's what's going to happen to all your points. So let's go and change these all. Let's start with 0, 1, our intercept. X is 0, still 0. What happens to the 1? It becomes a negative 1 plus 3. It's me 2. So x is 0, y is 2. So there's where the intercept went to. Remember, it's going to look this way. So we're expecting that. Okay, let's try the point x is 1, y is 2. So if x is 1, we still got 1. Y is 2. I would have negative 2 plus 3, which would give me 1. And x is negative 1. I still have negative 1. And I would get negative a half plus 3, which would, I guess, give me 2.5. So x is negative 1, y is 1, 2.5. And we should see our graph looking something like this. So look at our transformed graph. Let me turn this off. Okay, we're back with a correction. When I put this point 1, 2 into the transformation, I got the point 1, 1, and then I graphed 1, 0 accidentally. So it should have gone in there, and now I erased my other one. What was it? That's okay. Okay, there we go. So, could you state the domain and the range for that new function? Okay, the domain is easy. It's exponential. It's always all reals. The range, well, because of the reflection, it's y less than 3, that horizontal asymptote, which on our graph we probably should have labeled. Okay, the other key feature of this graph is you ought to be able to label your intercepts. And I can see I got one right there. When x is when x is 0, I've got y is 2. What's my x-intercept? So there's my y-intercept. How do you find an x-intercept? Well, to find an x-intercept, you always let y equal 0 and solve for x. So here's a good review of algebra. I would be solving this. 0 is equal to 3 minus 2 to the x. We want to isolate the exponential. I'm going to add it to both sides. That is 2 to the power of x is equal to 3. When your variable is in the exponent, how do you solve that problem? You need a log, inverse of an exponential. So let's take the log of both sides. So the log of 2 to the x is equal to 3. How does that help me? Your power law for logs lets you know that x comes down in front. X times the log of 2 is equal to, oh my goodness, I took the log of 2 to the x, which means I did the same thing to the other side of the equation. Just a little spill. Okay, so x log 2 would equal log 3. Solving that for x, I get x is equal to the log of 3 over the log of 2. As in, to what power do I raise 2 in order to get 3? And that's a calculator question. You can plug that in and tell me what you get. 2 decimal places. It should be 1 point something. 1.58. Okay, so x 1.58 when y is 0 in our notes. Okay, so when you compared them and you just did that on your graphing calculators, 2 to the x started out bigger. Sorry, x squared started out bigger than 2 to the x, but as you go to infinity, an exponential function will always win. So 2 to the x grows more quickly when x is large. When x approaches infinity. Okay, we've seen exponential functions all kinds of places. Compound interest formulas. Do you guys remember your compound interest formula? Try writing it down. A equals P naught. Get you a start. 1 plus R over n to the power of n times t. What's the n? The number of compounding periods in a year. Okay, if you're looking at light transmitting through glass or water, the more panes of glass or the deeper the water is, the less light you have coming through. That's an exponential problem as well. Population growth. Do you remember your population growth or decay formula? Write it down. A is equal to P naught times R to the little t over big T. Little t is the actual time you leave the sample. Big T is the length of that R life. Okay, your base formula for growth, y equals a times b to the x. Of course, your base is bigger than 1. If it's decay, your base between 0 and 1.